Okay, good morning, everybody. My name is Harry Ricker. This is the Cosmology discussion group for April 19, 2026. And I hope everybody had a good week. It was nice and warm here. It was like summertime, hot, kind of real hot. Okay, looks like we got everybody here. So this week I suggested that we were to discuss Pierre Robitaille's um, theories or ideas. And I think the best thing that we could say about Pierre Robitaille is that he's really um, kind of refuted every cherished belief of astronomers, pretty much everything along the line. He's really put out a series of videos where he really challenges everything that they believe. And I think it's important to realize that these ideas are over 100 years old and haven't really been significantly modified since the 1920s. That was 100 years ago, wasn't it? Yeah, I think so. And we haven't had any significant changes since then. So, of course, science seems to be more based on once somebody has claimed to have proved something, we're going to hold on to that belief no matter what. And that seems to be the modern scientific method. Einstein's theory of relativity being a pretty good example of that. You just can't shake the foundation of belief that goes on. So, did anybody have any comments about Robitaille's videos that I sent out? We discussed this topic last week. Nobody has anything to say. That's interesting. Um, so I'm not sure where we should start.
No, that's a
Okay.
good question.
All right. I guess that leaves it up to me. So Robitaille has basically presented a thesis that stars are not balls of gas. Um, and that he starts off with that main um, objection to that. And that's been around, I think, for a very long time. And I believe that idea goes back to, and I'm not familiar with the guy's name. I believe he was a Swedish fellow, where he studied the hydrodynamics of gaseous spheres, and I forget his name, but I believe that was in maybe early 19th century. And that idea, I think, got carried on by Jeans and Eddington. And you have this idea of the main sequence. Stars are on the main sequence. And so they did some early physics. And what Robitaille criticizes is the idea of this equation that defines the main sequence of stars. Now, I suppose that I should have had some diagrams here. Is everybody here familiar with what is meant by the main sequence?
No.
Okay. Are you familiar with the HR diagram, the Norris Russell diagram? So you're
Mm,
not familiar with that either.
mm.
Okay.
Russell
This is
Hertford.
Russell Hertzberg. I can't remember. Anyway, there's what's called the HR diagram, which is they plot the spectral sequence or the color of a star on against its luminosity. Now, I should have brought up a picture. Now, has anybody actually looked at these videos that we're talking about,
I did.
other than myself?
I went through them very quickly, mainly on double speed, actually, because of time constraints. But they seem to be saying the same thing, actually, basically, his thesis.
Yes, that's correct. I'm going to Okay,
Well,
so
I
the
would like
basic
to
bottom
point
line,
out, Harry, if I may, just an interjection. The videos that you sent around are a good reflection of what he's doing for sure. Good videos. But I also sent one out that is a very recent one where he goes into a lot of detail. I think that we can talk about here. One of the things is that he points out in the corona, for example, of a star, we see a huge electron deficiency. And that, just for a quick translation, he points out is a misinterpretation of a very high temperature. So, there's a lot of, as you pointed out, there are a lot of concepts that he really pushes over or uses a sledgehammer to crack them. You know,
yeah, that's one of the controversial. I want to talk about the main, his kind of his main idea, and this goes back to if you look at if you plot the Hertzsprung-Russell diagram, okay, for the closest stars, okay, those are stars that you can um, they can measure their parallax, which is you can measure its position as the Earth orbits around the sun. You can measure a parallax or a change in position, and from that they can calculate the distance. Okay, and so what they do is they then plot the knowing the distance, then you can estimate the brightness of the star. Now, then there's the other classification criteria, which is this is all very complicated, which is based on the temperature measurement, which is fundamentally what Robitaille is criticizing is the idea of a black body. Okay. And so what they do is they measure its spectrum, and from that, they determine its temperature based on the idea that the star radiates as a black body. But a black body is not a ball of gas. And this is really where the real problem comes in. So you plot the temperature of the star based on its measurement by spectroscopy, and you put that on this HR diagram, and you plot that against its brightness. And it turns out that most of the stars that are close to us fall on what's called this main sequence. They fall into like a well-defined curve, which is called the main sequence. And from that, um, they in the early days they basically developed this theory of stars as being balls of gas. But what has happened is that if you plot the brightest stars, not the closest stars or the nearest stars, if you plot um, the 100 brightest stars, you get a completely different plot. Okay. And part of it is an extension of what's called the main sequence, but you get a lot of these other stars. You get dwarf stars and what are called giant stars. So, what happened really kind of boils down to this. They had this nice physical theory called, the main sequence, where back in the 1920s, they could explain main sequence stars by simple physical equations. We can plot the luminosity against mass, and you have what's called the mass luminosity equation. And so then they were able to fit that equation to the plot of the main sequence, and they said, great, we have this wonderful, wow, our theory is confirmed. Therefore, this proves that stars are balls of gas. And so that kind of became cast in concrete. And Robitaille basically goes over this, and he sort of credits Eddington as the main culprit, if you will, in this famous book, The Constitution of the Stars, which I don't have a copy of, but it's a big, thick thing published by Cambridge University Press. And it's like 100 years old now. Okay. And they're still basing their physics on this 100-year-old theory. And Robitaille is basically tearing this theory to pieces because over time, what's happened is they've discovered there are lots of stars that are not on the main sequence, so they don't follow the simplistic rule that they developed in the 1920s. You have dwarf stars that are very underluminous, so they don't really follow the rule. You have giant stars that are more luminous than the main sequence stars, and then you have um, bigger giant stars, and then you have supergiant stars. And not only do you have stars that vary, that don't fit the curve, you have stars that don't fit the spectrum classification. Okay. And you have stars with these peculiar spectrums. You have stars that are metal rich stars. You have stars that are metal poor stars. You have stars that are magnetic. You have stars that are not magnetic. You have this tremendous variety of stars and it in all these different categories. Okay. And they just don't fit their simplistic theory that they developed, which is really just based on stars are gas balls, and that's their basic premise. And there's no proof that stars are gas balls. Not any proof of that at all. All they measure is what they can see on the surfaces of stars. We don't even know what's beneath the surface of our own sun. So this is just an hypothesis that stars are gas balls. And Robitaille is really basically challenging that idea. He says that there's actually a surface beneath the photosphere of the sun, which is the outer atmosphere of the sun that produces most of the spectral lines. And he's arguing that there's a, a I believe he calls it the metallic hydrogen lattice. I'm not really sure exactly what that means, whether that means that it's a solid surface or, it's not. He uses some terms that I think are kind of confusing. He uses the term condensed matter, and I'm not really sure what he means by condensed matter.
It would be
Uh,
considered solid for all intents and purpose, I believe.
Yeah, that's kind of my understanding of it. And yes, but I noticed in his videos, he doesn't really clearly define what that means. And he uses that term to describe planetary nebula and lots of different things, physics phenomenon. So his idea is that stars are composed, I think, of condensed matter. And he says the sun is a hydrogen lattice, which is an idea which really is so unfamiliar that it's really kind of hard to put, to really sort of, what does that really mean? Hydrogen lattice. I mean, usually you think of hydrogen as a gas, but apparently there's some justification for this viewpoint, which I'm not really clear on where it comes from. But I think the main idea is that the real problem, the real problematic idea is this black body radiation, this idea of a black body spectrum. That really turns out to be the major problem, I think, in astrophysics and cosmology, because they measure in the microwave spectrum this black body radiation of the quote Big Bang. How does a Big Bang create a black body radiation spectrum? I mean, I just don't get it. It makes no sense to me. And, it's just this perfect black body spectrum. And Robitaille says, well, when we actually measure black body radiation in a laboratory, it comes from carbon. Originally, the measurements were based on lamp black carbon or carbon soot. And so what you're really doing is you're measuring the radiation of carbon. You're measuring the spectrum of hot carbon. Okay. That's basically, I think, his argument. His argument is,
Well,
how did hot carbon become a gas in stars.
There's a little addition to it, which I pointed out that last video, the long one. He points out that the CMB seems to be directly connected to the oceans on the Earth emitting that specific wavelength.
Right, and they don't like that. And
No, but
because
there's I mean, he does make a strong case. I just wanted to point it out that, he explains it that way, as fantastic it may seem, but
yeah, and that's really, yeah, that's a fundamental one. Um, I think he's saying that because he thinks that black body radiation can't be produced by gases. I think that's the bottom line of it. His argument is black body radiation can't be produced by gases. Okay, how is that possible? And I find it kind of difficult to believe myself, quite frankly. I just don't understand it. I don't understand how you can get a black body spectrum from a theoretical entity that you claim existed at some point following, how many microseconds or whatever following this Big Bang thing. And, they have this complicated theory that's, that the radiation didn't escape until a certain point in time after the Big Bang. So you had this big fireball of hot radiation and hot matter. And at some point, the radiation became decoupled from the hot matter. But this hot matter, that whatever it was that existed, a bunch of pre-elemental atomic particles. This is even before I think atoms existed. It's hard to make any sense out of it, in my opinion. And then this created a black body radiation, but I don't see how that creates a black body. I mean, to me, that's just a fantastic speculation. Where does black body radiation come from? They just claim that a hot gas can make a black body radiation, but in the laboratory, it seems we can't really produce black body radiation from hot gases. I think that's kind of what his point is. Okay, no comment on that.
Just by the way, another point, does he accept the nuclear fusion origin of the energy produced by stars? You talked about hydrogen and helium.
I don't know. Maybe Ida could tell us a little bit.
I
Uh,
I don't think he addresses that topic too much, or at least not in too much detail, but I can be totally wrong there. He goes on about these other topics more. But I think he speculates or hypothesizes that it has something to do with the lattices there, because that connects again to the field of Lehner, if you will. That's why this is an important topic. You come into the on the field for mainstream physicists at MIT, etc., who speculate about, metallic hydrogen perhaps being connected to as to why the protons can breach the Coulomb barrier, all in the mainstream terminology, in order to do the fission, right? What drives the star. So it is an important topic there, Harry, but I don't think he goes into too much detail there. What I would like to point out, and that's why he connects it with quite a strong case he makes in that interview to the oceanic water, because what he keeps pointing out, in my mind at least, is spectroscopy, and they give telltale signs as to what's going on. So meaning there's not a really hot corona, but, electron deficiency. We see the black body created by a lattice structure. We see a different lattice structure at white dwarfs. So there's a huge misinterpretation as to how dense it is. The CMB is a completely different origin, and including in this whole spectral analysis that he, like no other, can give, he points out that even things like the redshift is inherent to specific chemical connections and bondings and whatnot. And I forgot the detail there. But just to throw out how destructive the man is for standard model cosmology, if you will. And I personally strongly resonate with his ideas. And yeah, fusion, that's a whole different topic. Yeah.
Okay. Made a pretty simplistic um, overview, I think. Um, the basic astronomer, the main tool in the astronomer's toolkit, there are really kind of a couple of tools. One of them is the law of gravitation, in which you make measurements of positions and you calculate based on the Newton's law of gravity or Einstein's general relativity theory, the motion of the planet. Okay, and then they've extended that to stars. And so that's one of their main tools, but that tool doesn't really operate as far as what happens in the stars. And so their main tool is spectroscopy, where they measure the spectrum by spreading out the spectrum using a prism. And I guess Newton was the first one to do this. Um, I guess he's credited with that. Supposedly he had a hole in the wall of his room and put a prism up at the hole of the wall, and then showed that the light coming through was broken up into colors. And that's attributed to Newton. And I'm not really up on the history that follows that, but then you have these spectral lines. I think Fraunhofer is famous. That's why they call them Fraunhofer lines, for discovering that the colors were there were dark lines in the different colors. So the spectrum of the sun is broken up into different colors. And then you have these lines, these dark lines in the sun. Those are called Fraunhofer lines. And then, of course, in the 19th century, they were able to identify these lines with elements. And that's kind of interesting because when you want to identify, I remember when I was, a kid, you would put a chemical in the Bunsen burner flame and it would turn green or different colors. Okay. And if you look at those with the spectroscope, you get spectrum, what are called emission lines or bright lines. So the light comes off, it's not a continuous spectrum as a black body. A black body has what they call a continuous spectrum, but elements, when you heat them up, they produce emission lines, and they're discrete lines. And this leads then to quantum mechanics theory that explains this, the origin of these spectral lines. But you have dark lines in stars, and you also have, which are called absorption lines, because the idea is that the atomic transitions are absorb light from underneath, or they're upper in the photosphere, and they absorb light that's being produced beneath them. And so you have absorption, what they're called absorption lines. And then you also have emission lines, which are bright lines. They're not dark lines, they're bright lines. And so you have these two types of emission of, of spectrum lines, emission lines and absorption lines. And one of the things is that astronomers kind of have a neat way of explaining it. But what it really turns out is that they measure stars that have emission lines when you'd think they shouldn't have emission lines. And then you have stars that have absorption lines and emission lines at the same time. That doesn't really fit into their model. So their model is kind of a mess when it turns to spectroscopy. And so it's not really a neat picture. That's what I conclude. And of course, I understood this for a long time. It's not anything new that Robitaille is telling me about this. It's kind of a mixed bag of stuff. And they sort of use a lot of ad hoc assumptions to explain away, these different star measurements that they make on stars. And it's a wide variety of stuff that they found. So they have their classification of stars, which you would think that starts off with this very simple thing. They're borrowing the principle, I think, of like, say, from botany. We're going to go out and we're going to classify plants and animals. You have a classification criteria, and then you have cats in one category, and you have dogs in another category, and then you have criteria for putting cats in, for saying this animal's a cat and this animal's a dog. And they did the same thing in astronomy. And what they used was the black body temperature and the spectral lines that were detected. And so you have this classification system, O, B, A, F, G, H. I can't remember all of them, but you have the mnemonic, O, B, a fine girl, kiss me right now. I don't know if people are familiar with that. That's supposedly the mnemonic for remembering them. And it's very
Same as the musical
confusing.
scale, I think. I think
Yeah.
that's where it probably comes from as well.
Well, the mnemonic is "Oh, be a fine girl, kiss me right now." Now, I think in the beginning they had this classification, which was A, B, C, D, and then later they changed it to make it a temperature scheme. So, in other words, O is hot, B is after that, A I think it's it's OBA. It's very confusing because it doesn't follow the alphabet. But what they did was they changed their original classification so that it went by temperature. You understand what I'm saying? That's why it's not like A, B, C, D, E, F, G, H. Okay. It's O, B, A, G, and oh, be a fine girl, kiss me right now. And so the temperature classification by temperature didn't really agree with their previous classification ideas. And so they relabeled things, and it's made it kind of confusing. Okay, you have to really, be familiar with their classification schemes, and they've changed the classification schemes over the years. And I don't, when you look at a modern classification, they have these additional subscripts that they put into it to, make it a more fine-tuned classification. But anyway, the classification diagram, or the Hertzsprung-Russell diagram, is really based on the idea of temperature versus luminosity. So it's how hot is the star and how bright is the star. And we're talking like on an absolute scale. Okay. And so they get a nice thing where you get this what's called the main sequence, which is let stars congregate into kind of the middle of the diagram. But then you have all these outliers, and that's really where the problem begins. Where do these outliers come from? You've got these white dwarfs, which are really way under luminous. They're supposedly the size of the Earth, but they have the mass of the sun. And so they're said to be super dense because they're as big as the Earth, but as massive as the sun. So that's the fact that they're small is supposed to explain the fact that they're not bright. And then you have on the other end, you have these supergiants, which are supposed to be these huge, 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 gigantic stars that are very, very luminous, and they're very, very bright. So they are supposed to be very large in order to explain why they produce so much light. Okay, so the idea is that the size of a star determines how bright it is. So there are two things. There's the temperature of it, and then there's the size of it. Now, Robitaille is challenging the idea that the luminosity is defined by the size and the mass. which is based on the mass luminosity relation for the main sequence. And he's highly critical of that. So he's really going after some of the more cherished ideas of astrophysics and astronomy. He's really challenging everything that these guys believe, which I think is kind of interesting because not very many people are doing that.
I will add one more detail there about the white dwarfs. It's something that I really enjoy pointing out. White dwarfs are the size of the Earth, and they have more or less the chemical composition of a thing like an Earth. So, in my mind, um, you know, could be a
That's a,
solid body.
yeah. Now, I've never really bought this idea that stars are bags of gas. I never really thought that. That's why I like Vadimir's WUM theory a lot. That really attracted me to Vadimir's thinking on this subject because he doesn't view stars as gas balls. And it never really, I never really thought this idea made a lot of sense. And I didn't understand. The other issue is Robitaille basically uses thermodynamics, and he proves that there's no way that stars can condense from gas clouds.
Right.
And he does a very good video on that. I've never believed that. You can, I mean, I just thought that was the most absurd thing. How do stars condense from gas? That just seems to me thermodynamically impossible. And I read a lot of books and a lot of papers about this. And after years of looking at it, I decided that this whole idea was just impossible. You have the angular momentum problem, okay, which Vladimir has talked about here quite a lot. That doesn't make, if the gas cloud contracts, you assume there's no angular momentum in the cloud, in which case you get no angular momentum at the end. And then you also have the problem that you can't explain how the planets form because they're supposed to form out of this disk that's spinning around. And so you have to have some angular momentum at the start. But if you have a little bit of angular momentum at the start, you wind up with too much angular momentum at the end.
And the distribution of the elements doesn't make sense in my mind as well. Why would the hydrogen go to the center to form a star and the heavier ones form the planets? If you put that in, why not the heavier elements at the center?
Yeah, that's a good point. And it's just more of why it just
Right.
doesn't make sense. And
Well, the main point I pointed that out, that planetary body as a replacement for a gaseous white dwarf, if you will, Harry. What I think Robitaille is pointing out through his research, backed up by a lot of spectroscopy that he uses as his tool, I take a lot of, I give it a lot of credence, if you will. And the really main takeaway point is, as you pointed out already a couple of times, stars are not gaseous balls. They are likely, at least that is then my opinion, I guess, a way more complex system where you could have solids, liquids, gases, plasmas, magnetic fields, electric potentials, fusion, fission, and all the lot going on. And at least in my mind, that is what it's betraying. And sure, you can have classifications. But as long as we stick to that 120-year-old idea, this field is not going to progress a whole lot, right? So, yeah, this is the main concept I think we need to do away with. Stars are not gaseous balls. They're way more complex. So that's the only thing I really wanted to shout out here. Thank you.
well, that's my view too. And as I alluded to previously, that's one of the things that attracts me to Vadimir's theory. Vladimir has developed a theory in which that's one of his main ideas. And he tries to start off from the beginning. He rejects the Big Bang. And of course, the Big Bang is really basically has to, if you think about it, once you've accepted the idea that stars are gas balls, then and then you accept the idea that gravity is the main force in the universe, which that's why they love general relativity. And so that's their two main tools, remember, are gravity and spectroscopy. So their theory of gravity is the main tool that they use. And they've adopted Einstein's version of the gravity theory. And so then they discover, oh, hey, this gravity theory says that the universe is expanding and over time, it's not a static system. And so they got that idea. And so then now you have to have how do gas balls uh, form from something that is at the beginning. And so then you have this Big Bang idea where you have this fireball of elementary particles being created and interactions. And it's kind of hard for me to really, I can't make any sense out of it. It just seems absurd, absurdly ridiculous on its face. And I don't really understand why they don't realize that it's absurdly ridiculous on its face.
Well,
Um,
if I may throw in a comparison example from the quantum mechanic realm, if you will, as you know that I do not consider the neutron to be a fundamental particle, and that is like cussing in the church. And well, here's the thing: this is historical, and we're trying to write a paper about this whole topic. We hope to make it such a level that we can actually, throw it out to the world. But the neutron was accepted as a fundamental particle when it was detected, and there's really something there, and it's electrically neutral, and all that good stuff. And then for the development of the quantum mechanics that was developed, in I think in the 20s, 30s, previous century, around that era, for coinciding with the neutron observation, the finding of it, it was very handy if the neutron were a fundamental particle, and lo and behold, that's what they found. But the free neutron decay came later, the observation of it. But by then, the neutron was already accepted as a fundamental particle within the quantum mechanics. So it's like difficult going back on that decision. And, in my mind, that is exactly what's wrong here. And I think a good example, and that plays out in a cosmology realm as well, with the stars being gaseous balls, is another example. Once that decision was made, we stick to it, as you pointed out in the beginning of this talk. I don't know how to resolve that one, but we see it all the time. So how can we make progress? It's kind of my question I'm asking here.
yes, well, I think Pierre Robitaille has sort of tried to really point out these things. I think the issue really, and I guess people don't like me to say this, but I think there's a real problem with science. And this is people not necessarily in our group are really promoting this idea, particularly people who object to climate change. They think that science is just a joke that's being used, and primarily because the proponents of climate change who have gotten into the political system and imposed all these regulations on people that are ruinous to economic progress are really basically that's justified by it's the science and the science is correct. But it's turned out their predictions don't work. They've been predicting, for years that we were going to have, horrible consequences of climate change for God knows as long as I can remember, since I was in college, which was a long time ago, and it hasn't materialized. And so they're questioning the value of the scientific method and how. So we're not the only group that's questioning the way science is being done and the way science is being used in society. Um, the climate change people are they're sort of happy because they think they're winning the argument now.
Well,
Uh,
there are still dissidents there too. I'm one of them. The climate change arena, I think you pointed it out very correctly, very aptly. Um, they simply abused the scientific standing, if you will, to promote a political idea for their own benefit. And who and they and the benefit are is for everybody to sort out here. But they abused and misused science here, if you will, promoting it as a scientific method to sell a certain idea. But if you dig into it, they make rookie mistake after rookie mistake. That was for me in the beginning when I was exposed to this a few decades ago, quite amazing. And you go like, how can they make these mistakes? And how can they say this? And how can they say that? And then later on you learn, well, that is, because we want a specific outcome. That's all. It's politicized.
right. And I think that this is kind of the issue that we have about whether science is about challenging accepted ideologies. And it seems, that that's not the case. That adherence to the primary paradigm is rewarded, and objecting to the primary paradigm is not. It's discouraged. And so I think that explains a lot of what we see in the Robitaille videos, particularly where he points out these papers that give these conflicting conclusions. He's very good at pointing out how, this paper says this, and then this other paper published by a different person, doesn't agree with the first paper. And then there's a third paper that doesn't agree with and it just goes on, and they don't really deal with this issue of why don't all the different measurements agree. They just publish the papers and get a citation, I guess, and can put that in their CV and present that to the promotion committee of their universities. And that seems to be their main objective. They don't seem to really be that interested in, dealing with the fact that their measurements don't agree with each other.
See, this is the problem we have in the dissident community, in particular, what you talked about a moment ago, like climate change and so on. You see, one can understand, maybe not applaud, certainly not applaud, but one can understand why certain ideologues would use science for their own benefit to prop up their own prejudice and so on. One can understand that. But it's quite alarming if one comes to the conclusion that scientists have betrayed the trust that we've put in them, because they've gone along with the political fashion of the time to suit their own careers and their own advancement. And they haven't actually stood up for strict scientific principles. And what they're doing is accepting something, maybe which is ideological in origin, but once it becomes the norm of society, then scientists go along with it. So they've actually been treasonous to their own science. And then they're using ad hoc hypotheses. Something I was reading the other day is they were measuring, there was two people or something about the pneumonia vaccine or something, and one didn't get it and one did. And the one that did get it got pneumonia. And she said to the doctor, look, I've got. So the doctor just dismissed her right away. He said, well, that proved it worked, that you got pneumonia, because you'd be dead if you didn't get the vaccination. So they're
Yeah,
twisting things around, and this is the problem we have. And I suppose Robitaille is bringing it to our attention, so at least that's of some benefit.
If you look at the climate change 10, 20 years ago when it was promoted very much, you saw a news outlet, and it still goes on, proves climate change proven this, CO2 levels that, alarm here, alarm there, more storms, blah, blah, blah. But then what did not come in the big highlights, in the big the headers on the newspapers and whatnot, was that there were petitions signed by 2,000 or 20,000 scientists, actual real scientists, signing a petition for, arguing exactly against, for example, man-made climate change. So what I'm pointing out is there were way more people that thought differently, dissident, if you will. But in the media, you get a very different picture just because, they can throw out what they want to throw out. But the reality was that on the grassroots level, most people that were involved in that science pointed out this is not true, this is not correct, etc. So yeah, just so, but the science did get a very bad name, and that's why I said it's taken for a ride. It's used, it's misused. They were not even real scientists. They were people like an Al Gore, right? He's not a scientist. He's a politician.
Well, we also have the pandemic, which the Corona pandemic, which that didn't really help a lot of the so-called doctors who were telling us what to do and
Same
how to
story.
do it, and claiming that it was all based on science. The science says this. Okay, and so I think there's my thesis has been that science claims things that they really can't prove. And one of the, from the very beginning, I always thought that this idea of um, stars or gas balls, hot gas balls, never really made any sense. That the idea that they can condense from the solid objects like planets could condense from gas clouds, that's just absurd. I just I don't understand it. I don't see how they can even entertain such a silly, absurd idea. And um, I think it's just basically this idea. Laplace, had this thing called the nebular hypothesis, and that they just can't say that they can't break away from some traditional ideas that are just don't make any sense. Because it makes them look like they know what they're talking about when they say, "Oh, well, the solar system condensed from gas clouds in interstellar space." Well, how did the gas get there? Oh, over time, the stars created elements in their interiors through nuclear reactions, and then they explode in supernova, and that spreads out the elements into the universe, and those elements condense to create stars that then creates more elements, and then they explode, and we got more supernova explosions, and so we got this recycling. And isn't it amazing? We're all stardust. As soon as I hear the stardust, then I think this is absurd. We're stardust. That's absurd. It's a joke. And it's astounding that people believe it.
It's even been used as an explanation by fundamentalist people, when they're asked, for example, God created light, but that was prior to his creating the sun. So where did the light come from? So the answer that frequently is given, the nebula hypothesis explains it all. That was the light first.
Yeah, I think the religion issue is kind of, that arises, the religion, the whole Genesis thing, people believe that who are religious. They want to believe it. And I can understand why they want to believe it, because there's a moral authority supposed to be invested in the Bible. So, and then science came along and tried to debunk all that, which I think was not really appropriate. But the real problem I have with science debunking religion is that there's no guarantee that science knows what it's talking about. I mean, that's, as far as I'm concerned, scientists have no authority to say that religion is wrong. Their thing is a lot of ridiculous nonsense. A lot of science, stars are gas balls, and the universe was created in a big bang. And then the religious people say, aha, big bang, that proves Genesis was correct. We just were misinterpreting it.
See, to a certain extent, they're Tweedledum and Tweedledee. the religious people became political. Religion became political, and became something just to advance power and so on. And it had no regard to truth.
You're
The
referring to the
scientists have done
Catholic
exactly the
Church.
same. The scientists are
You're
criticized, and they've done exactly the same. They've become
Well, that's
political.
one of the things that Robitaille says. Robitaille says that science is religion, and he talks about that. I did notice that he brings that up in his talks, and and other people have pointed this out too. Maybe not necessarily Robitaille, but the climate change people or critics are saying that science is like a religion. It, it it's believed because it's just a belief system. It's not necessarily correct. That's Robitaille's point, is that modern science is a belief system. It's really based on belief. It's not really based on any real facts that proves that it's true.
And of course, the commonality between the two is that they're both based on authorities. You have approved authorities,
Right,
and
which the problem has to do with the Catholic Church. And once the Catholic Church became a large institution that had money and lots of control over the over government control, because you know um, Charlemagne became the first Roman emperor. He was crowned by the Catholic Church as the first Roman
Parliament is based on
Holy Roman
Constantine.
emperor. Okay, so that gave the civil authority, even more authority. It had the authority of the church behind it. And I can understand in the Middle Ages why the Catholic Church was kind of important and needed, because that was education. That was where people got educated, and a lot of economic. The monasteries produced a lot of economic products. So it's important to the economy and to learning, and one can understand all that. It makes sense. Um,
And
but
perhaps it's not surprising if one considers organized religions to be man-made and science as man-made, the propagation of science. Well, then they would both be subject to the same foibles and organized systems of control and authority, as I said. Perhaps it's not
right.
surprising.
Well, the issue with Robitaille, I think, is that he's challenging the fundamental physical ideas that they've basically held on to. And it's kind of interesting, particularly the one about the white dwarfs, I think is interesting, in that they say, well, the white dwarf has the mass of the sun and the size of the earth. And being the size of the earth means that it's extremely dense. And so therefore it should have a very high gravitational field strength, and we should measure a gravitational redshift. And then he goes into excruciating detail of their attempts to measure the gravitational redshift, and pretty convincingly shows that it's not really a conclusive argument, because of all the discrepancies that he points out in their measurements. If you measure certain spectral lines, you can claim there's a redshift, but if you measure other spectral lines, there's no redshift. So what's going on here? And of course, they don't want to go in their final reports of their papers and say, well, our measurements are inconclusive because we've got all these discrepancies that we can't explain. You don't really publish a scientific paper that says that. You have to basically publish a paper that has a conclusion. And so that's what they did. They say, well, yeah, we discovered gravitational redshifts and we confirmed the theory is correct. But, Robitaille then looks at the paper and says, this paper doesn't agree with this other paper. And there's all these discrepancies, but nobody seems to want to basically resolve the discrepancies.
Incidentally, just as a matter of interest, do you know anything about Robitaille? I mean, he's not gainfully employed, is he? How can he?
I don't, that's a good question. I don't know.
Right. Just wondering how he has the freedom to say all these things.
I don't know whether he's retired or, um, I don't even know whether he's associated with the university. I don't really know. Um, so that's kind of an interesting question. I had actually thought about that, but I didn't get around to looking into it. Um,
I think he comes from the private sector, or at least with a very strong spectroscopy background.
yeah,
So
that's what I thought too, but I wasn't really. I don't really know for sure. Um, I don't think he's an academic. That's I don't get the impression that he's an academic. Because to explain what you're saying, Ian, is if he was an academic, he couldn't be saying or publishing these videos that he's publishing, because the way I understand academics, I have a friend of mine that's a professor at the local university here. And from the impression I get from talking to him about the way things work, if you say something that really is controversial, it's considered to reflect badly on the university. And in the particular case of the university that we have here, they're in trouble financially. And apparently, all the universities are in trouble financially because of the decline in enrollment, because of the demographic shift of enrollment. So they're jealously guarding their reputations. And particularly the university here is not highly regarded in the state of Virginia. This Virginia Tech that I went to is considered to be, much more popular. And apparently they're worried that they're not getting enough students. And so if you don't get students, you don't get money. And if you want to attract students, you need to have a good reputation because they have these ranking um, methods. If you don't get a high ranking, so there's a lot of pressure to conform. And my friend is under a lot of pressure to conform to, particularly to the prevailing um, doctrine that is promoted by the academia. So that's a big negative incentive to do dissident science or try to promote ideas that aren't within the mainstream established viewpoint.
So perhaps paradoxically, the places where the mind is trammeled, is straightened in the greatest degree is actually in the universities where there's meant to be free thought and expression of opinion, but also in the private sector, which I think Ido mentioned. I mean, if a company thought that its sales would be, negatively influenced by employees holding particular views, that could be, a restriction on views. So I think perhaps if he had worked in the uh, private sector, he may be retired now and doesn't have that impediment.
I would think so. That's a good issue to look into. Um, I, I I don't know. And apparently nobody here has an answer to that question. So that's a good question.
Okay.
I guess we
the
pretty
people
much.
that I talked to a couple of weeks ago that are running startup companies in the field of low energy nuclear reactions tend to be, engineers and whatnot, usually from the private sector. And when you ask them about, transmutations or the method of this or that or the underlying scientific support, I usually tend to get an answer that, they don't really care. That they look at things very differently. They understand the importance of it. That's not the case here. But they also understand that science is not the end all and be all, that there are very different viewpoints, and that science doesn't understand everything. But they work with practical results. Engineers or chemists, if you will, whatever. And so yeah, so they treat this very differently, I would argue.
Well, being an engineer, I understand that perfectly.
Right, right.
I mean, as an engineer, I look at these scientific claims and I think that doesn't make sense, but nobody's paying attention to me. um, you know, that's why one of the things that we've noticed is that there are a lot of engineers in the dissident community, particularly electrical engineers, are critics of special relativity and Einstein. And one of the things is when as an electrical engineer in the communications industry, one of the things that I had expertise in was setting up networks, communications networks, and dealing with the issues of time. You have to synchronize these networks, and so that communication, so that different digital terminals can talk to each other. And as soon as I started hearing about Einstein and relativity and all this other stuff, I thought this doesn't really make any sense. If engineers paid attention to what Einstein says, then nothing would ever work. But they don't. That's the whole point. They just go and make it work. And that's what they did for GPS. They just made it work. It's like they didn't pay attention. And then later, the physicists all said, oh, it uses Einstein's theory of relativity, when the people who set it up and designed it really didn't. They only used general relativity. The general relativity says the clock should change by this much. Okay, so the clock's going to slow down due to gravity, so we'll just tweak it so it runs faster. That's the engineering solution.
Well, engineers change the world.
Yes, and it's a right. It's a different thought process, and then the physicists, they have this ideology that they're trapped into. You have to, we have to obey these laws of physics, which are cast in concrete. And one of the things I think is kind of interesting, which you brought up, which is the idea about the neutron being a fundamental particle. How can a particle be fundamental if it decays into two different particles?
I keep pointing that out, sir, but they keep telling me I see it wrong. So,
Yeah, and I can tell you for a fact that that bothered me you know, um, since I graduated from college. I mean, that I pondered upon that mystery for a long time. That never made any sense to me at all. Why you could consider a neutron a fundamental particle if it decays into two other particles? What's that all about?
well,
Yeah,
that's from as far as we could find, yeah, historically. The neutron was observed by Chadwick, and the mass determination happened. Now, first he determined it to be lower in mass than the proton, and 1 or 2 years later, he determined it to be higher. And there was a whole debate about it at the 1933 Solvay conference as well. Quantum mechanics was in development and strongly proposed by all the culprits back then. I always point at the Danish friend. Now I forget his name. Good show.
Bohr.
I forgot his name just now, tip of my tongue.
or
But Niels Bohr, thank you. By Niels Bohr, and basically he was one of the dominant types back then, and the quantum mechanics development would be very grateful, let's point it out that way, if the neutron were fundamental. And that's what won the day. It was useful and you could calculate so well then. I don't know how or why, but that was sort of the argument. And the neutron decay was established later on. So the decision should have been reversed, but it's kind of like, could I have back that Nobel Prize, please? So yeah, yeah.
that seems to be the problem that
Yeah, yeah,
I think Robitaille is pointing out this issue, which is we can't we can't change these fundamental ideas. In his video where he talks about the mass luminosity equation developed by Eddington, and he takes a lot of this to task. A lot of these fundamental equations of astrophysics that were developed in the 1920s, for goodness sake.
yeah.
And when they didn't know anything, they're just speculating about what's going on and what is a star. We're speculating about what the physics of it could be. And he says that a lot of the assumptions that are going into their equations that they're using are just they're not supported by thermodynamics, which I find interesting. So you have he's sort of saying, well, I understand thermodynamics, and thermodynamics doesn't seem to agree with the physics, astrophysics of stars. And just there's a big disconnect between these two scientific disciplines. And it kind of, if you think about it, if I was an astrophysicist, I'd say, somebody please shut this guy up.
So let me
Because
complicate the matter just a tad there with the neutron and connect it to cosmology and the function of stars. Um, Now, as you pointed out, this stuff was all pretty much determined 100, 120 years ago, and we're still stuck with that. Now, the neutron is important in the Big Bang because allegedly most neutrons were created in the Big Bang. But when we look at the function of stars, you have a proton-proton reaction that makes a deuterium. Hence, proton changes to neutron. But that allegedly doesn't happen a lot. Then you have the CNO cycle. The CNO cycle turns hydrogen once through all kinds of intermediate steps into helium-4, creation of two neutrons. And if you look at the reactions, there are problems there on how to do that. So the neutrons, perhaps if we just postulate the neutrons were all created in the Big Bang. And then later on you start to understand the function of the stars where neutrons are created. So it starts to contradict. That's the problem with the models. But so to point this out, this ties to the functioning of stars. This ties directly to the Big Bang model. This ties directly to fundamental nuclear physics, which has something to do with the plausibility, for example, of a thing we call cold fusion, just to point one out. So everything ties into everything here, and quantum mechanics development, relativity development, cosmology, if you will, the Big Bang scenario, the neutron acceptance, all these things happened 100 and 120 years ago. That's what we're fighting still.
it's cast in concrete, yes, because you
Yeah.
have it's a religion, it's turned into a religion. The establishment is fundamentally based on these pillars of ideology that can't really, they don't want them to be challenged. Um, and the way you teach it, I think, is once you've created an idea that science has all the answers in the way they present science as if it's true. We know that stars are gaseous spheres. And how can they know that? There's no way they can know that. How can they know that?
So I'll
Um,
give you one personal thing. We long learned that through the work of the structured atom model with the nucleus and neutrons not being fundamental, that we would not be very much accepted, yeah, in any way, shape, or form. We get that. Okay. For once, we did try to turn in one paper that was based on a presentation about the structure of the nucleus, so not focusing on the neutron whatsoever, but, the fundament is there. And we tried to get a paper into the fringe community accepted to be published in the journal there. And the first one was kind to us, so supportive of the idea, the first reviewer. And the second reviewer was very much more adamant and mainstream minded and simply stated that the neutron was accepted and proven to be a fundamental particle, Harry. So paper, we can't do this. So I withdrew any attempt to any paper publishing ever again. And instead, we simply wrote a book about it far easier. But this is the resistance you run into. Yeah.
Well, you got gatekeepers in it, and so you wonder. I can understand, where you'd have a gatekeeper, like you have the Rick was talking about the people who believe in the flat Earth, and that's kind of ridiculous. And you know,
Great.
if you just let those people just publish in science journals and everything, that's kind of, I can see where the line has to be drawn at some point. But there don't seem to be any judicious rules about where the line should be drawn. They don't, they've decided that we're right and we know everything. That's I forget the famous quote from where we know everything. So Feynman, I think, had some quote about this. We know everything already, so we don't need to. No new information is needed. We already know everything.
Right, there you go.
Well, that was perhaps referring a bit more to Kelvin and people like that at the end of the 19th century. But I find it intriguing how these orthodoxies, which you're talking about things that happened 100 years ago or 120 years ago or more, have subsisted. It was actually Max Planck himself who said new ideas really require the previous generation who held contrary ideas to die out. So it really takes, say, 70 years before you have a new departure. But things that have developed long before that are still being defended by the newer generations of scientists, of academic scientists. So they have a system, they develop a system which is rather self-perpetuating. I mean, if you take communism, if you like, took 70 years, the Marxist, Lenin, you daren't criticize it. But then after 70 years, those people had died out, so you had a new generation. So people start having doubts. And maybe the same has happened in some aspects of organized religion. But these scientific revolutions that took place maybe at the beginning of the last century, it's amazing, intriguing really, how they've subsisted. I think there is a little more, a chink of light under the door now than perhaps there was 50 years ago. They're saying now that in the 1950s, if you criticize Einstein's theories, there was no comeback, you were out the door. Whereas now there is a slight possibility you might be considered a bit of a crank. So maybe the thing is evolving very, very slowly, but it's still intriguing.
Right. Well, I don't want to make this sound like we're just, we're complaining because nobody pays attention to us. I think the issue is that there are. Vladimir, turn off your microphone.
Yes, I'm here. I'm here, sir. I'm sorry. I had to leave for a couple minutes.
Okay. All right, we're coming up. I think we got 6 minutes here before we get to the end. Was the issue I thought that I think we sent out. I think we covered some of the ideas that Robitaille was talking about. He has, I think, one of the main problems that resistance, as far as the mainstream is concerned, is he's attacked the cosmic microwave background radiation and claims that it comes from the oceans of the Earth. And I have to admit that I find that to be very I just find it hard to accept that that could be the case. And how could they make such a spectacular mistake?
You can't pinpoint the source, and it's all around us.
Yeah, I think that's what his argument is. Yeah, the real issue, I think, though, for me, is I don't see how and I think this is what his point is, although he doesn't really come out and say it. How does a hot gas produce a black body spectrum? I don't think he believes that that's possible.
Is that provable by experiment in your mind? I mean,
Well, you would think that could be proved in a laboratory, but I think his position is that the proof is otherwise, that the actual
either way, yeah.
laboratory.
Well, either way, what the proof is, but just to make a conclusive assessment there.
Well, again, you seem to have another example of an experiment which is interpreted in two contrary ways. It's not that we lack experimental data. We've done experiments, but the interpretations are quite at variance with each other.
Yeah, that brings up the issue of I think, which is in my mind the real problem with science, which is that they don't acknowledge that there are multiple interpretations. So they don't really, in the scientific method, all you have to do is have an hypothesis and then take some measurements and demonstrate whether your hypothesis or your predictions based on the hypothesis agree with the measurements. And if they agree with the measurements, then your theory is valid, then it becomes accepted science, and then you can't change it. But what if there's another hypothesis that would give the same results and also agree with the measurements? And they don't deal with that as a possibility, that's not possibility that's even entertained. And so what happens, and I think in the case of unipolar induction, which I've looked into very carefully, it seems that there are multiple hypotheses that can explain the data, but none of them really very satisfactory. So how do you um, how do you how do you deal with the issue of what of the many hypotheses that you could have that might fit the data, which one is the best? And what they've selected is the first one. The first one is the best one. We're going to stick with the first one that we came up with.
And then they
That's
frequently justify the rejection of alternative hypotheses, which, as you say, Harry, will fit the data just as well, by saying, oh, they're philosophically unsound. So in other words, give an example, they've dismissed maybe Lorentzian or Stokesian, ideas of the ether, which will give the same results as maybe Einstein's theory with regard to looking at Michaels and Morley or something. They say, oh, they're philosophically unsound, so we better take the more philosophically sound one. But it was formed in the first place by the mechanism that you just described. It was really the first hypothesis which was accepted.
Well, I think what Ito has pointed out is once they accepted the idea of a neutron being a fundamental particle, and then contrary evidence arose, the result was to dismiss the contrary evidence because it's our idea, the first idea has to be maintained against all comers. I'm not really sure why I understand they do that. Why is it that you can't admit that you were wrong?
Well, this is the birth of the particle zoo because a proton decays into a neutron and a neutron decays into a proton, and then both are a fundamental particle, right? So that's the
Yeah, that
start of the
doesn't seem
particle zoo.
logical.
Well, I mean, this is how they explain it away. And again, sir, I think we're in full agreement. How can it be fundamental if it's not fundamental, really, right? But yeah, there you go. I'm having that argument myself still with them.
See, somebody like Brian Cox, who one might take as the spokesman for the mainstream, he said that, oh, you might be able to explain this phenomenon in another way, just as satisfactorily. But you must remember that the whole of science is a big monolith and all the pieces fit in together. And if you reject the view in one respect, it's going to upset all the other.
I'm not getting a warning that the meeting is about to end message, so we have to be a little got to bit you again. Okay.
I think I've more or less finished, actually. I was just pointing out that the conventional view, as expressed by people like Brian Cox, is that science is one big monolith, and all pieces fit in together. And if you upset one part, you've destroyed the lot. So that's how he justifies accepting the conventional views with regard to any particular aspect.
Well,
Especially
yeah,
the neutron, I found out the neutron is very sensitive in that sense. You touch the neutron, you touch, many scientific fields at once immediately, hence the resistance. Yeah.
well, it's even relativity, special relativity, and relativity is another issue of that type. The whole thing, they don't see, um, I guess I'd put it this way, they don't see making a modification that clarifies and makes things clearer and removes the illogical issues that arise. They don't see that as a benefit. And that's particularly true in special relativity. They don't see cleaning up the illogical statements that, these paradoxes, it's full of paradoxes, and they don't see cleaning up the paradoxes as being a benefit. They've turned them into, lessons for the student to better understand the theory. That's kind of how they approach paradoxes. So they don't really clean them up. That's what I think is happening in your case. There are too many other impacts that would happen. We'd have to change all these textbooks.
Yeah. Yeah, that was a conclusion we drew as well. If you think it through, that is what would happen, and you would have to change a whole lot of textbooks and implications of it. I understand that, right? Intellectually, I totally get it. But opinion-wise, if you will, then that's just a personal thing. I think, the scientific method should have win the day, if you will, in the end, regardless of, yeah, okay, you have to change the textbooks. I get that, but a bit embarrassing maybe, but
Not to
Well,
change, guys, not to change, to rewrite totally from the very beginning.
that's
Don't
good.
try
That's probably
to.
better.
It's
Probably.
right. Well,
impossible.
yes, that's true. Yeah.
It's exactly what I'm doing for 25 years, everything from the beginning. Stop Big Bang, stop this nebula hypothesis, and all this stuff. And the same story with all the branches of physics. You must do principally new picture of the world, new physics, new everything. Don't try to change. Brian Cox, he's right. If you will change one point, you must do something with the same point, with the other point, and so on and so on. Nobody will do it. Now instead of physics, we have political religion. That's it, simple like this. We have a new Bible, physical Bible, and we are trying to change something. Forget it. It must be everything from the beginning. It's exactly what I started 25 years ago to think about. There is no gas sphere. It's impossible to collect all your molecules together. There is no way. All these molecules must go around because around there is a vacuum. And all these molecules must go not inside of this nebula. Simple like this. Simple question. The next one, we have vacuum. Forget. We have our microwave background radiation. We have intergalactic plasma. It's confirmed experimental. Nevertheless, in general relativity, we have a vacuum. And, no logic at all. At all. That's why don't even try to correct something, to do something about it. There is no way. You must do everything from the beginning, from the very beginning, from the very first point, from the first ideas. That's
Yeah,
it.
from
That's it.
observation. I totally agree, Vladimir. We need to start from
That's why,
observation,
Edo,
real
you're
observation.
doing great job in quantum physics. I have no idea about quantum physics. I am working with classical physics. What is important? Don't try to promote only one your experiment, your idea, and start to think about from the very beginning. From the very beginning, that it is not okay. It is not classical article. Okay, if not, what must be changed in quantum physics that it will be a part of it. Simple as this, guys. You cannot
Well,
rewrite,
that's
do something,
that's
something special, something, one detail. No, you must do everything from the beginning.
That's in response to you, Vladimir. You just tickled my mind there. That is exactly what I have started thinking about since 2006. And that led me to the structured atom model, which, if you think about it and put it in your terminology, there would be a replacement or a rewriting of the whole quantum mechanics there. So,
Quantum mechanics. I absolutely sure with it. Mechanics is a wrong
yes,
physics.
yes,
Wrong.
it's
Absolutely
wrong.
wrong. There is no space, there is no time inside of quantum physics. That's why when we're talking about some dimension size, 10 to the minus 20 of something meters, it's bullshit. There is no even size in here. There is no time, there is no space, there is no gravitation there. Because gravitation, it's a classical physics. Classical means ensemble of particles. That's why, please start thinking about not how to promote this idea or that from the very beginning, basis of the quantum physics. That's what must change. And I bet you're absolutely right. Planetary model of atom, absolutely wrong. For 120 years ago, it was correct because there was nothing. But now we have so much information about. We
Yes.
must do something based on experimental results we have
Mhm.
now, 120 years later. That's why we cannot use old-fashioned quantum physics, classical physics, because I don't know,
Well,
guys.
not to promote my own stuff here, but this is exactly what I've tried to do because I fully agree with Vladimir's statement here. We have so much more knowledge, so much more observational data, so much more experimental data. That's why I started, or not didn't start, but in what led me to the elements, if you will, the most basic stuff, and redo the whole work there. I fully agree there. And I think, yeah, this is the best way to describe it, Vladimir. The old ideas were based on a very few little things, and we know so much more. So we only have to redo it with what we learned. And then we come to different models, different conclusions, and maybe the next generation will have their comments again. So be it, right? That's progress.
Not immediately, because you don't know how much time it left. I started 25 years ago. That's why what I'm talking about, it's my life for 25 years. I started to ask these questions about nebula hypothesis and all this stuff. I have no logic with them. I have no ideas with them. And then, I've done something in my life, more than 100 papers I published, by the way. Right now, I have a new one. That's why maybe next time I will share my latest paper with you guys. It will, okay, let me finish and then I will start to talk about. That's why, it's a long way, but everything from the beginning. Put all the knowledge, theoretical, model knowledge outside of your mind and start thinking from about a new one, totally new one. Ideas, realization of them. It's exactly my point, my life. It's not point. You have experimental results in front of you. Myself, for after 25 years of cosmology. And what is important, by education, I'm a laser physicist. There is no connection between cosmology and laser physics. Nevertheless, it came to me to start cosmology, and I've done what I've done, guys. Everything from the very beginning.
Okay.
Oh,
And one of the reasons we're having this discussion group is because of the your model, and we started off talking about your model and your ideas, and that was really when this group started.
but what is important, I've done already with Ian, at least maybe 12, sessions. We have with you, I've done so many reports at your group, and what is important, no response. People, they're looking at my papers there, but there is no comments. Nobody wants to follow because political chemistry, political religion instead of physics right now. People, if they will follow somebody's idea like myself, they will lose their job. If in a university you will not follow the standard physics, you're out immediately. I have at least two guys who was thrown away from university because they have their own ideas, simple like this. You can do your ideas, new one, only if you are independent. You don't have even money on your ideas, as it is myself right now. I work as a laser engineer. I developed new lasers for medical applications, but cosmology I've done overnight as a hobby. This is exactly what I will recommend to you guys. Don't waste all your time on special relativity, on quantum physics, on whatever. Everything obsolete, everything. Physics must be brand new. All the physics. That's why this is my point. It's exactly what I'm trying to do in my classical physics field. Everything new.
Okay, we've had that. I think we've talked about this with Robitaille and what is whether he's an academic or whether he's retired or what. Obviously, he's started off with this Sky Scholars. It's an impressive series of videos that he's done, and I think it's really um, uh, it's worth looking at them. I think for one issue, I think they're really over the head of the average person who's not really an expert on astrophysics. And then I think also for a lot of these people who know about astrophysics and understand what he's talking about, I think they're not really receptive to his ideas. So I'm not really sure what his audience is, who's really paying attention. People like me who are already converted. I'm already converted. I don't believe that stars are gas balls. I don't believe any. I don't believe any of that stuff. So he's preaching to the choir when I see these videos. I mean, I go like, right on, because I don't believe in
That is
gas
true.
balls.
That is true what you said there, Rick. But throughout the years that I've been doing my own journey, if you will, and I guess that's true for everybody here, I've seen an uptick in these types of videos. In the beginning, that was very obscure, if you will. But there's quite a big base out there internationally, globally, of people that do search out alternative information very much. And I think that particular group is very much a growing group, if you will. So there are a lot of people looking for this alternative stuff because many lose their faith in science because of climate change and the COVID and the whatnot, right? People lose their faith. And so they're hungry for truth still. I guess that's a human trait there. But I think this group is growing, and those are the people that are looking at this stuff, and people like you and me and everybody here.
Right. I do agree. What you're saying is that there's more of the internet and YouTube and
Yeah,
has made the flow of information a lot more um, simpler and different opinions are allowed. I'm not really sure how long that's going to last. They're
that's
going
a
to
good
allow
point.
this to happen. Um,
That's true.
uh,
Question. Somebody follows your ideas. But tell me, do you have anybody who understands your idea and share them with you? Do you have somebody? One. Because I have somebody,
You're
he
asking.
2 years ago, he done great job for me. My model must started to be more clear because he asked me very good questions. Harry, thank you so much for that. Thank you very much. Then Nick, he done a great job. He invited me to you guys, to your group, to your society, and I'm so happy to have somebody around to talk about my ideas and so on and so on. That's why, guys. But do you have either, or you have your own ideas and that's it, nobody else?
My work is carried by other people as well.
And then do you have a group to talk your ideas together, like we're doing right now in our group?
Um, there's, well, let me refine that. There's a couple of people that are absolutely convinced of the work that I do, strong enough to support it and work with me. So that's a small inner group. There's quite a strong fan base, I noticed by now after a couple of years. So many people in, just people watching it wherever they come from, supportive of the idea. So that's happening, and I'm involved in workshops and conferences, and right now in this group right here. So I do feel that I am making a headway and making progress. And yes, to an extent, there are definitely people that buy it, if you will, support it, and I can talk to, but not so, yeah, somewhat so. That's the answer.
I do want to
The
make
slight caution might be, sorry if this is a bit negative, is that we all might be given a slightly false sense of security because we come together at the weekends and we have a chat and I think we're all objective people and we might not always agree, but we appreciate each other's views. But then we go out onto the real world and we find that we actually are considered as crackpots. Not to put too fine a point upon it.
Yeah, but you can ignore that.
Yeah, I do. I try to ignore it. Yeah.
Well, I guess the reason why I'm explaining my position there, also to Vladimir and now to Ian, is because what I'm trying to say is I am looking for the interaction in multiple fields, multiple arenas from people everywhere. I don't care that much. I've even had interaction with the mainstream people, so professors at renowned institutions and whatnot. And they tend to be less receptive, but even there, every now and then you run into a person that's open-minded, and then it's a joy to exchange ideas. And I believe, along the way, if you keep, explaining an idea that jives with people and, keep doing it, might change the world
yeah,
somewhat.
I think that's a key point is making people familiar with these ideas. And for instance, the idea that a star is not a ball of gas, that's really kind of a radical thing for people that have been propagandized for years and years and years that it is a ball of gas. And they talk about it as if it's a fact. My main complaint I have with mainstream, and particularly the mainstream education system, is they present a lot of speculation as if it's fact. There's no proof that stars don't have a solid interior. There's no proof of that at all. Yet they just assume that it's so. What gives them the right to do that? And then they teach people that they know things that they don't necessarily know. Like all this business about nuclear reactions and stars, that's all theory. It's all just speculation on their part. There's no proof behind any of it.
You're absolutely right. You're absolutely right. Either I am so impressed with your standpoint. Atom theory, wrong. What is your theory? What is basis of your approach to quantum physics? Can you share with us in our group the beginning of your theory, not the result of it? What is your understanding of atoms, particles, and all this stuff? I will be more than happy to hear your report.
No, I'll be happy. I'll be more than happy to do a presentation as
Please
such.
do
It's
it.
somewhere
Doing
down the
this
road here,
presentation because
but let me give you a quick answer too. Yeah, quick answer. What I consider the most fundamental parts of my model is this. There's only one particle, that's the proton. Arguably, there's another particle we call the electron, even though it's a quite mysterious, nebulous thing, right? Now, we know a few things about them, and my basis is this. These two particles is what forms a nucleus. As we know, the neutron decays into proton electron, so there's no neutron there. That's the first difference. So only proton and only electron. The protons make a structure by a self-organizing principle simply because of the electrostatic attraction forces. It becomes self-organizing. And that I found out through long search and detail and comparing and whatnot, that there's a progressive growth in a specific manner, which is a very organic lookalike manner or a crystalline lookalike thing. So the nucleus is something like a complex molecule in structure, actually. And when I found that growth pattern, lo and behold, all the numbers of the periodic table completely fit, including explanations such as why something is a noble element or something has an oxidation value of such and such. And so many correlations with the actual physical attributes, if you will, chemical and physical physics. So the basis is that that's the organ. There's an actual structure in the proton structure held together by the electrons, and there's much more detail, in a specific growth pattern, and that totally interacts and jives completely and explains even why the periodic table is as it is. And then there are many other things, and we try to put all that into our book, Vladimir. So there's a lot more that this is just quick and dirty.
It's
Yeah,
exactly
that book
what
is
I hear, but
pretty
not the
detailed,
whole book.
actually.
Oh, I'm so sorry. Sorry.
No, please go,
You know,
Vladimir. I did not catch it.
let me tell you, you cannot present to us the whole book. My main point is ideas, basis of your new approach. Start point. What your start point? Because in my model, I have intergalactic plasma. Of course, you must have proton and electron. This is a part
Okay.
of my model, no doubts about it. But
Mhm.
I have so many different atoms, I don't know how to name particles, so
Do you
named
mean the
universe
creational
created particles.
aspect?
And do you have them inside of your model? Because there are so named dark matter, dark energy, it's
Ah,
95% of our matter in the universe. And I
okay.
doubt that there is even way avoid these particles inside of quantum physics as a particles.
Okay, let me point this out. Everything I've done in the structured atom model, and I am writing a paper out of mass of the neutron talking about fusion, fission, and the release of energy, absorption of energy, how that works in detail. And that has everything to do with what you just stated there, because what I show is, for example, that the neutrino is not really needed to explain nuclear reaction energy-wise. So
You mean
it falls off.
neutron?
No, neutrino,
Neutrino.
Okay.
neutrino. So
Oh, okay. That's another.
there is no need for a positron because the electron is not poof, whisked away, doesn't exist in the nucleus in the standard model. In my model, it simply exists in the nucleus in a different state, carrying more mass, exactly 0.782 MeV. Some may recognize that number. So it's not whisked away. So there's no positron. So there's no neutrino. All that stuff is suddenly gone. What I'm trying to state is everything I've done, I can do what you can do in the standard model nuclear physics, I can do too, and explain a whole lot more, including nuclear fission. But there is no need whatsoever for antimatter, neutrinos, antineutrinos, and all that good stuff. There's not even a need for it. There's not a hint for it. All that magical stuff falls away. So you don't need 12 dimensions. You don't need
Oh, yeah.
impossible. It just drops off. So it becomes very much, I would argue, real, real science again. Real politics, real science, It's all gone. All that mysterious stuff is gone. There's no dark matter, no dark energy. Well, look, I cannot exclude, like I said, definitively doesn't exist this or that. I'm not trying to be that definitive. What I'm trying to say is all these things we can do without the need for these concepts and make it horribly difficult and mysterious or magical even.
I
Let me
think
ask
they
you the
like
question
it to
about
be that
magnetic
way.
field. Either. What about magnets? Magnetic fields. how you going with magnetic?
That's a difficult topic, Vladimir. I'll say that up front, but it seems to be connected to what we call the proton.
Has a magnet, what it has as a particle.
I, whew,
Yeah, oh,
that's
it's a good point, you know.
no, well, no. I like your question, and I think we can formulate an
You
answer. But
cannot
you're putting
avoid
me
this
on the
question,
spot
you
here.
know.
I find it
Magnets,
difficult to
they
formulate an
exist.
answer right now.
Yeah, magnets, they exist, and you must explain magnetic phenomena too.
Yep.
Well, there's a big bugaboo there, Vladimir. You certainly pointed that one out. Um, the thing is, if you're saying it, and I think your assertion is starting from scratch, and a large part of the problem, I think, is that electricity and magnetism is a well-established theory that's off. That's in a different silo from the silo that Ito is talking about. Familiar with that term silo that Charles Lucas has talked about. You have the different disciplines in science, and they don't talk to each
Different
other.
disciplines. You're absolutely right. Totally different. As I told you, particles, it's one story. Ensemble of particles, it's another story. Classical physics, ensemble of particles. Electromagnetic theory is for classical physics only. When in quantum physics they use all these laws of electromagnetism, it's absolutely wrong. You cannot do it. Because classical physics, it's ensemble of particles, ensemble. For each particle to talk about Coulomb law, about magnetic field, electric field, there are no, these are the classical notions, even fields. No,
Yes.
that's why you must do something about magnetic field when you have ensemble of your protons, ensemble of whatever. Only then you can talk about these notions, even definitions. That's why, guys,
In my mind, it
avoid
starts
in
with charge.
classical, in quantum physics, avoid all these classical notions. Avoid. It's forbidden for you. Don't even name them.
Yeah. Um, I did want to mention here, you have this, they have this new thing that they're talking about now, are magnetars, which is some kind of a magnetic star. Like, where did that come from? That doesn't really fit into anything that how do you get a magnetic star out of a ball of gas? I mean, gas doesn't really, one of the things about magnetism is gas doesn't have magnetism as far as I know.
Yes. Yes. And that's why it's exactly my point. When you're talking about particles, take into account that when it will be ensemble of particles, it must be some magnetic phenomena, classical, and the big story particles, original particles, ensembles of these particles. That's why you must take into account this possibility later with your particles, with your approach to go to classical physics based on ensemble of your particles and explain for us why we have magnets for thousands of years. Thousands. People, they
Yeah,
know
No,
but
about
I
magnets.
think
believe it or not, I fully agree with you, Vladimir. But for me, mind you, this is a journey, and I am doing what you said. I call it a clean slate approach. I even gave it a term there, right? Start from the beginning, clean slate approach. Nothing is sacrosanct, and it's a journey. And for me, I found the structure of the nucleus connected to the whole periodic table, but that was without having established fundamental physics, if you will. So after that, the story became for me automatically, okay, how does that connect to the most fundamental physics? That's what we're talking about here. And that is still an ongoing journey, if you will. So we started with masses and the particles and the structure, how that translates to nuclear reactions, so the whole nuclear realm, fusion, fission. Now we think we have that down now, more or less. That's why we write a paper about it. And now come the other challenges, which are legion, and they're all big topics. And Vladimir, you pointed out a very important part there, for sure.
Yeah, the issue I think is that as dissidents, we're not really working in a cooperative manner. These are problems I think that need to be solved by groups working
Yes.
together. And the issue is that the way of organization is usually orchestrated by money, and the money is not controlled by people who are interested in this project, a dissident project of science. So the money is not flowing to support what our ideas are. So there's no real cooperation. You can't. Usually, you get people to cooperate by money. It seems to
That,
be
well,
the
that's
main
because,
function of money.
yeah,
Huh?
well, I would like to, I always used to think like exactly like that, Harry, but I also found that the money provides hierarchy. Hierarchy means I can, as the boss, push through my opinion, and then lo and behold, that's the outcome, right? But that would be just one of the many dissident opinions. Again, so what I'm trying to say is perhaps a true alternative thinking might emerge if we find a way to cooperate despite the lack of money.
Yeah, that's a challenge. Agreed. And yeah, um, obviously,
Money is important
whoever
though.
controls the money, unfortunately, gets to control belief,
Sure,
and
that's true.
that's the danger there. Um, there are a lot of issues here. I mean, you know, yeah, it's just you, I can, as we discussed earlier, the Brian Cox argument that, well, we don't want to change anything in our established views of science because we'll have to rewrite all the books. And think of all the people that would be involved in coordinating to rewrite the books. That's the whole educational system would have to basically rewrite their standards of education. Think of the massive bureaucracy involved in changing anything.
But wouldn't that be
I
a
mean,
better employment system than the military, for example?
Yeah.
Hmm.
I have a friend of mine that he's on a committee for the state of Virginia talking about changing the Virginia textbooks. And apparently, you have to go to meeting after meeting and discuss it and months and years and all this stuff just to make a minor change in the curriculum. The amount
Well,
of effort is,
that should be the triumph of science. If you found through the scientific method that what you said previously is incorrect and has to be revised, that should be a very exciting project. Science
Yeah,
should not be a chore. They're taking it as, oh, a terrible thing that would be an impediment on our time and a very laborious and boring endeavor. Science should be the opposite. It should be exciting. And we should be delighted that we're now having to rewrite all the textbooks and start from scratch.
well, yeah, you would think that they would think about it that way, but that's apparently not the way they. I think they're more interested in it's my ideas that need to be in the revised textbook rather than that guy's ideas.
Right.
I think that's what the issue is.
Mm.
I noticed
yes,
that
that plays a role.
Roger Penrose says that quantum mechanics is wrong. I find it interesting that he's come out with a blanket statement like that. And you'd think that a lot of other people would be saying, great, this is a big opportunity for us to invent new science, create new science, invent new things, create all this new stuff. But no, they're not interested in rejecting quantum mechanics. They don't see that as an opportunity. They see that as an impediment. So why, anyway, we've got very few minutes left. I'm sorry to get on that soapbox.
I mean, it's the well-known thing. If you obviously think of an elderly person towards the end of his career who spent all his life teaching a particular scientific system, he's going to rebel against having to revise all his ideas. That's the human trait.
Yeah, I know. And I watched Ivor Cat fight with those people and for years and years, and Ivor Cat, he just struggled and or tried to coerce them to stop thinking in your very old-fashioned hidebound, obstinate way, and they just really couldn't. They didn't get the message that they were being obstinate, and they just refused to entertain any new ideas, any new thinking. They just wanted to
There's a
stick with
well-known
the.
there's a well-known quotation from Tolstoy, which you may have seen, to the effect that it is well nigh impossible to get people who have spent their whole lives teaching a particular doctrine to others and have woven that into the fabric of their lives. It's well nigh impossible to get them to revise their views.
Yeah, I think we know that
You know
to
the
be
quotation,
true.
don't you? Yes.
So we're talking about we're coming to the end. So I'm going to say we talked about Professor
Uh-oh.
What are
issues
you?
with astrophysics, and I think that I focused on the main one, which is stars are gas, composed of gas, and it looks to me like that premise is not very flexible. They've really gone as far as they can go with that premise, although they've done a pretty good job, I think, of inventing a lot of ad hoc hypotheses to explain the origin of elements by creating these ideas of the nuclear reactions, and different nuclear reactions result. And this gives you different types of stars. The star moves around on the Hertzsprung-Russell diagram based on what nuclear reaction is happening in its core. And then, of course, you get the penultimate when you run out of fuel in the star, it explodes in a supernova. Star dies, and its remnants are spread out into outer space to create new stars. But there doesn't really seem to be any way for new stars to be created. And the real issue that I think he attacks rather convincingly is there really isn't any way for stars to form from gas. It just, he claims it's thermodynamically impossible. And I generally think that's correct. That's a really pretty astounding conclusion that you can't really, you have no real good theory to explain where stars come from. So your whole imaginative structure of cosmology and astronomy and astrophysics and everything about science tells us where we come from as human beings just kind of like falls to pieces. And I can see why there's a resistance to what Robitaille is saying, because if you accept his thesis that he's proved that stars cannot condense from gas clouds, that just destroys everything in cosmology and astrophysics, and just throws out science root and branch. So that's a pretty significant thing that he's doing. It's impressive. Okay, I don't think we have less than a minute. Want to
Yeah.
thank everybody participating today, and hopefully you've enjoyed it, and we've had a good exchange of views. Thank you for coming, Ido, and telling us about your ideas. Very, very interesting. Um, okay, I want to finish by saying we don't have anybody. I'd like to have somebody to volunteer to lead the discussion for next week, and that would be nice. And I noticed we didn't have a discussion yesterday. I don't know what happened. There wasn't any Saturday morning discussion.
Well, very, very briefly, I was scheduled to give this talk. Well, tomorrow.